So we found out with systems that graphing was not necessarily the best strategy because we couldn't always be precise with our graphing, and we couldn't always figure out the exact point where they intersected without using some sort of graphing calculator, whether it was a program or whatnot. And, oh, papers to pass out. Thank you. And then we found with substitution, we needed a certain way that our equations looked. We always wanted to have a variable that was either by itself already or one that didn't have a coefficient in an equation that I could solve. Go ahead. And, but that's not how everything is given to you. So what I want to share with you is a new strategy when the equations don't meet what the other types of problems look like. So this new strategy, and this is from lesson 6.3, is called solving systems using elimination. So what is it that you would see in an equation or a system and you'd say, elimination is going to work. So the whole point is we realize we cannot solve an equation that has two unknowns. So we're going to somehow have to get rid of one of the variables. Well, with substitution, we were able to substitute in a value for one of the variables so that all I was left with was the other variable, and I could solve a one variable equation. We've done a ton of that. So for this one, what I want to look for and there's two scenarios. So the first one I'm going to give you is...
You said to look out for, so I thought that
no.
these was what you looked out for.
What you want to look out for that's best is same variable, same coefficient, opposite signs. So I know if you're saying, hey, how can they be the same and be opposite? What I'm talking about is the numerical value solely, and then we'll look at signs separately. If you have same variable with the same coefficient but opposite sides, I can now add my two equations together. Bam! I've eliminated that variable. Okay, so yeah, it's pretty cool. So we're going to add the equations to eliminate or remove, basically, that variable. And then we're left with one variable to solve for. We solve for it, and then we will be using substitution, obviously, with our answer into either original equation to figure out the remaining variable. And then we write our ordered pair as, you know, x value, y value, okay? That's the best case scenario. The worst case scenario, which is not horrible for us, we won't call it worse, that's terrible. Let's call it good. We look at this, find a same variable. They have the same coefficient numerically, but they have same signs. If I tried to add two values that are absolutely identical, does it eliminate them? No, it doubles them, right? It makes them bigger, so that's not successful. So we're going to have to do a little prep step, and then we'll be able to add them. Now, the book calls this using subtraction. I don't think it's really using subtraction, to be honest with you. What we're going to do is multiply, and here's where choice comes in, one equation by, and what could I multiply an equation by so that a same variable with the same coefficient but same sign, how can I get their signs to be opposites? Yep. I'm going to multiply one equation by -1. And then add the equations to eliminate that variable. So I just do a prep step. And then it looks like what I did before. So it's the same notion of adding the opposite. We can force it to be opposite. Patrick.
So you can't divide, you can only multiply.
Oh, you can multiplying by -1 and dividing by -1 is exactly the same thing. So that step of changing the signs, it's either operation works. Now, what the book will show is that they may show subtracting that whole equation, and then they'll distribute the negative. And so that's why they use multiplication. But again, multiplying and dividing by -1 is logically equivalent. So it'll get you the same thing. So let's practice this so you see what we're doing. And so directions are going to ask us to use elimination to solve. And remember, all solutions, to a system is going to be an ordered pair. Or if we get something that doesn't make sense, could be no solution, or it could be infinitely many solutions, depending upon the answer we get if the variable gets completely eliminated. All right, so let's do first one here. 4x plus 6y equals 32. 3x minus 6y equals 3. So again, I'm only going to use this technique if my equations are set up to use it. So I quickly scan and I look at my x's. Do they have the same coefficient? No. So that throws it out of the running. How about y's? Do they have the same coefficient? Okay, they do. Now, so I have the same variable y, same coefficient x, or 6. Now my question is, how about signs? They're opposite. So this is the best case scenario. Because what do I get when I add opposites?
You get 0.
That's right.
So eliminates the equation.
So this is best. Yay! So what happens when I add 4x plus 3x, combine like terms, we get 7x. The y's are opposites, so they zero out. On the other side, I get 32 plus 3 is 35. And I'm left with this one-step equation to solve. Divide by 7, x equals 5. And then I'm going to substitute this back into either original equation, it does not matter, and solve for the y-coordinate. So I'm going to go here, I don't know why, because. So I get 4 times 5 plus 6y equals 32. 20 plus 6y equals 32. Subtract 20 from both sides. 6y equals 12. Divide by 6. And I get y equals 2. So right now, I have an answer of x is 5 and y is 2. So I can test this. Again, I can always do a check. Checks work. So is 4 times 5 plus 6 times 2 equal to 32? And we get 20 plus 12 equals 32. And we get 32 equals 32. So it satisfies the top equation. Now let's try the second one. 3 times 5 minus 6 times 2, does that equal 3? So I have 15 minus 12 equals 3, and I get 3 equals 3. So it satisfied the other equation. So that verifies that's the correct answer. Okay, so again, some people go, I love this. The problem is not all equations are going to work for this strategy. Okay, so we only use this when it's the perfect timing. All right, let's keep trying. Let's do some more. Let's do one. This one's kind of interesting. Oops, sorry. I don't want purple. I want black. So we've got 4y plus 3x equals 22. And we've got 3x minus 4y equals 14. Now, what's a little bit confusing about this problem?
It's flipped.
Yeah, we've got things organized differently. And so what I can do is take one of the equations and use a commutative property, and I can change the order. So you may have to do that small alteration to then quickly check your x's and your y's. So my x's, Ooh, look what you get for your x's. Same variable with the same coefficient, but same sign. So that's good, but it's not best. So I'm going to keep that in mind, because if I multiply everything by -1 in one of the equations, then this will work. Let's look at the y's. What do you notice there? Same variable, same coefficient, different signs. That's the best case scenario. So guess what? I don't need to do any alterations in terms of multiplying by a negative. This, again, is going to be my best case scenario with the y's. So when I add the two equations together, 3x plus 3x is 6x. The y's give me 0 because adding opposites always gives me 0. And I add up over here and I get 36. Divide both sides by 6 and I get x equals 6. I'm going to take that value and I'm going to substitute it back into either original equation. Really doesn't matter which one. I'm going to go here. And I get 4y plus 3 times the x value 6 equals 22. So I get 4y plus 18 equals 22. I subtract 18 from both sides, and I get 4y equals 4. Divide by 4, and I get y equals 1. So right now, it looks like my solution is 6, 1. But again, I want to make sure that I'm doing it right, so I'm going to check. So 4 times the y value, 1, plus 3 times the x value, 6. Does that equal 22? So I have 4 plus 18, and 4 plus 18 is 22. So it satisfies the top equation. How about the second one? 3 times the x value, 6, minus 4 times the y value, 1, equals 14. So I get 18 minus 4, and I get 14 equals 14. So it satisfies both, and so now I'm confident with this one. Okay. All right, let's do one where they don't match. So what is that going to look like, and how are we going to handle that? So we have 2t plus 5r equals 6. This also brings in the notion of no x's and y's. How do we handle that? 9r plus 2t equals 22. So how do you think I'm going to write my ordered pair using these variables? What do you think the answer is going to be listed as? What's going to come first? Remember, alpha order. So we would go alpha order with our variables. But nice try.
Thank you.
All right, so this is kind of like the last one. The r's and the r's don't match up, and the t's, they're kind of diagonal from each other. So I'm going to, here, arg. I'm going to rewrite this is 5r plus 2t equals 6. Okay, so we look at our r's. Do we have a match on our coefficients? Okay, throw him out. So we go to the next one. We've got a 2t and a 2t. Fantastic. What about signs? They're the same. So this is not the best. This is the good situation. So here's how I fix this. It doesn't matter, but I'm going to multiply one of the equations by -1. That gives me negative 9r minus 2t equals negative 22. So because this was the good situation, we had to do a little bit more prep work. So now this one is gone, right? And it's been replaced with this one. So now we're ready to add. Signs are different, bigger numbers negative. I get negative 4r. My t's are opposites, so they eliminate. Here the signs are different, bigger numbers negative. 22 take away 6 is 16. And then I just divide both sides by -4. And I get r equals 4. And now, you guys are so sad. And then plug this into either original equation and solve for t. So 5 times 4 equals 6. So I get 2t plus 20 equals 6. Subtracting 20 from both sides, I'm going to do it up here. And I get 2t equals negative 14. And then divide by 2. And I get t equals negative 7. So again, we're going to write alpha order, r and t. So we get 4, -7. And again, I would go back and test it to make sure that my point is right. So that's the fun bit for tonight.